Hello, I'd like to finish up the data link layer now. The last video I did on this, we talked about the media access control. The media access control is the part of the data link layer that connects to the physical layer. Above it is the part of the data link layer that connects to the layer above it, which is the internet layer. So I'll just make a comment here. The logical link layer is between, and I should call it sublayer, because it's not a separate layer, it's part of the setup here. It's part of the data link layer. It's called the LLC. Is between the network layer and the MAC sublayer. So its purpose is to fix it so the Mac doesn't have to worry about all the different possibilities that could be available on the internet layer. It makes it so that the Mac has, no matter what kind of LAN it's on, the Mac only needs one interface, the interface to the LLC. So no matter what kind of LAN we are using, the Mac only needs to connect to the LLC, which is the same, no matter what, is the same for all the different kinds. Now, there isn't much I can say about this, because the biggest problem for us, for trying to describe it, is that we don't use it much. It turns out that the LLC is really not used by Ethernet. I do have here from the 802.2, I think it is, or 802.3. This shows you the Mac client. The Mac client, in most cases, is the LLC. But for the Ethernet, it may actually be the network layer itself. There's two connections up to from the Mac client down to the MAC, and from the MAC up to the Mac client. So the internet has something to send. It's packaged it, ready to send it. It sends it down to the LLC, which interfaces it, does whatever needs to be done to make it look the same in all cases, and sends it down to the media access control. Now, the media access control seems to have some strange things connected below it. As near as I can tell, what we're looking at is 4 sort of indicators or variables and 3 conditions between the two. So the 4 variables the Mac uses to know what's happening on the physical medium. The carrier sense, remember we talked about that when we talked about internet. That means that the Mac can sense what is on the bus or the satellite. Collision detection, which means it can hear if something is wrong. And receive data is valid. so it knows it's receiving the proper setup. The fourth variable, I think the physical layer gets from the MAC, and that is whether the MAC is transmitting or not. Now, there's three other items there, and they're the things the MAC could be doing. It can be transmitting a bit to the physical layer, receiving a bit from the physical layer, or essentially idle, waiting for something to happen. Now, Ethernet does not use an LLC. It just didn't feel it was necessary. If we had different kinds of implementations of a local area net, then we would need an LLC. In fact, there's many, many different LLCs. The Internet Standard in this particular form, I have it pointed to it here. I thought I had pointed to it there. No, it doesn't seem to want to come up. Let me try it again. I think I got it this time. It's huge. And this is only, this is the standard for Ethernet. And if you look down here, I'll get past all the names, you can see just how much is involved with this. It talks about the basic functions. The collision handling is here. As you go further down, we have the different medium attachments, what to do with optical fiber, and it just goes on and on. There's so much there. It even gets into the physical signaling, because remember I said that Ethernet breaks the rules. It covers much of the three bottom layers. So I also excerpted from it the packet format for an Ethernet, and you can see the various pieces of it. And that's about the best I'm going to say about the LLC. Now I'd like to talk about three physical items that sometimes get confused. They're the routers, the switches, and the hubs. We've mentioned routers a lot, and I'll get to them in the last one. But I want to start with the hub. Remember that we have to be able to hear the message anywhere we are on a LAN. And as the message goes further along the LAN from us, it weakens, it attenuates, it's not as strong. Well, there's a limit. There's some point beyond which it's too weak. But if we want to have more computers connected, we can't connect them directly to the same bus. If we do, the signals will be too weak. So what we do is we put a special device in called a hub, and all the hub does is it takes what comes in on one line and shouts it out on the other line. It repeats it. That's all it does. It's like a person who's getting in a message and then yells it through a megaphone to the other side. Both sides, because it goes both ways. So it doesn't have much in the way of intelligence. Its job is just to amplify the signal it gets in. What this does for us is it allows us to have bigger internets, bigger LANs, pardon me. There's still a limit. They usually have a limit on how many repeaters are allowed. The reason for the limit is that if you remember, we have to have messages long enough so they go across the entire internet and still are interfering with something that started at the other side. So they basically have to fill the internet. And if the LAN. And if the LAN gets bigger and bigger, they have to get bigger and bigger. And we don't really want that. Now, a switch, what it does is it takes information from one side and it forwards it to the other side. It is at layer 2. It uses the memory, media access control addresses, the MAC addresses. It connects LANs. It has a table of MAC addresses to determine which line to send the message on. It can send out op requests to find out who's there, who has a particular address. Now, it doesn't go up to the rest of the network. In other words, the messages here are for our neighbors on the LAN. And we don't have to worry about sending them all the way up to the top. They're just going to go across at layer 2. A router is a layer 3 device. Its job is to figure out routes of the network, remember. It has a table that tells it where to send things. That table is created by the various algorithms we looked at earlier, including the Bellman-Ford algorithm you wrote. And the big difference is it's at a higher layer. And it's sending messages farther along. It's not just sending messages within the LAN. Now that's what I want to say about that. I have here too, there's a huge number of transmission media we can talk about. And I got this from, I think it was Geeks for Geeks. They talk about the various types of media we can use. The wired media, they call it guided, and it's not just wire, it could be optics. And the satellite, the unwired, the microspace, whatever microwaves, whatever. They are, one item is called a twisted pair cable. It's basically two wires that are wound around one another. Actually, and that way, it's the most widely used way to do it. And there's two types of them. Unshielded twisted pair just means that it has the ability to block some interference. It does not depend on a physical shield to block it. And it's used mostly for telephones. Least expensive, easy to install, high speed, but it is susceptible to external interference. And it's got a lower capacity than compared to the shielded twisted pair. The shielded twisted pair is inside something. It has something that protects it. That's used in the data rate Ethernets and in voice and data channels, the telephone lines. Now, the advantages, better performance. It does a better job on crosstalk. It's faster. But it costs more. And that's the problem. But neither of those are really what we would love to have. Well, I guess, pardon me. Coaxial cable, it just means that the outer plastic covering containing two parallel conductors, each having a separate insulated protection cover. It transmits information in two modes, baseband or broadband. Cable TVs use this. It has a high bandwidth, better noise immunity, inexpensive. Disadvantages: a single cable feature can disrupt the entire network. Now we get to what we really would like. optical fiber cable. And you notice the word optical. I hope you know what that means. We're talking about glass. We're talking about using different forms of glass media to send information. It uses the reflection of light. And it could be plastic instead of glass. But we are using light to send things. Now, light's fast. And there's got to be some cladding around it to protect it. The best part about this is that even when we get it in the ground, we can fix it without taking it out of the ground. We can change things about it. It's got better protection against electromagnetism. It costs money, and you have to spend more time installing it. We put it in the ground, not across the wires, I guess. So, well, I guess we could put it across the wires. Those are the ones I want to talk about. There are more here, as you can see. Radio waves, microwaves, infrared waves. Now, there's a huge number of groups in 802.3. 802.3 is the Ethernet's actual description as it's used in the OSI model. It differs slightly from the official Ethernet, but it's slight. Now, let's look at what I have here on this one. Sure I can get it. All right. Just look at all of these that are going to be coming. It's showing you some information, and then it shows you where this fits. We're going to talk about this 10 base 5 and 10 base F in a minute. So there's lots, if you see IEEE 2.3a, for example, is for thin coax cable. 3I is for twisted pair. So there's there's one for each of these, each kind of medium that we could use. I copied a few of those in here for you. It's important, it's good to know the pieces. You see these when you buy cables or when you're looking at different Ethernet cards or whatever. The convention says that there are 3 parts to our description of the transmission media. The first number tells us the speed in megabits per second. So this is only 10 megabits per second. This would be 100. We could have 1,000. The second term says whether it's baseband or broadband. That's technical. The last number is the segment length. How long can we make it? A 5 means 500 meters. That's the original ThickNet. In more recent versions, letters replace those numbers. The T means unshielded twisted pair cables. We have an F that means fiber optic. And you can see we define some of these in more detail. FX uses 2 strands of multi-mode optical fiber for receive and transmit. Maximum length is 400 meters. Then you've got SX, and you can keep going and going. If we were to be spending a lot of time in the physical layer, we'd have to look at those things, but I'm not worried about it. Now, we're getting higher. we're going into gigabit Ethernet. And this is 802.3 AB. And you see some of the things that it talks about and the different sizes there. In the 802 world, they started with the 802.1 and the 802.2 and so on. Now they're working on more complicated 802s for WiMAX, the maximum wireless. You'll see 802.16 or 17. The 802 standard from the IEEE is what is used in LANs. We aren't going to be talking about OSI or RFCs here. We're talking about IEEE 802. And as I showed you, it is a pretty complicated little baby here. If you look at it, it goes on and on. And you can see how many people were involved in it. The list is several pages long. And this is only 802.3. If I think I can show you the current, the IEEE 802 standards. And you can see here, is the ones, 19 is wireless personal networks. There are quite a few. And I think the list, I can get this list here. This is just some of them floating around. Look at them. I guess it's all of them. Cable modems, Bluetooth certifications, the 16s, wireless access, wireless convenience. You can see a lot of wireless is going on now. And they're all the way up to 24. This is not static. They're still trying to improve and improve. But I notice over here some of the upper ones are not working much. It seems that 15 is the only, the largest one that's really involved in anything. Now, that completes, I believe, what I want to say about LANs, and in particular about the data link layer. We've now finished the 4 parts of the TCP/IP model that are software. We started with the applications layer, which again connects a client and a server, or one app and another app. Then we went to the the transport layer, which connects one node, one computer to another computer. A destination computer to a source computer to a destination computer. Then we went to the internet layer, or the network layer. I keep calling that the wrong thing. It's the IP portion. And its job is to handle it all on the way. It goes from one site to the next site, to a neighboring site. And then below that, the final layer is the data link layer. And its job is to basically take what it comes from the higher layers and get it down to the physical layer that is going to send it out. The physical layer is the place where a lot of the hardware is talked about. So that's what I want to say about that right now. We'll see you later.